So scales are a structure that biologists have used for many years to study fish. They're equivalent or sort of similar to tree rings. As the fish grows in size, it's laying down periodically little rings along each of its scales. And as salmon hit the open ocean, they undergo a rapid growth spurt, and the distance between those spacings, between those growth rings, gets wider. And then when the fish slows down its growth, the spacing between the rings gets smaller. So from this information, we can tell whether a fish has spent 1 or more years at sea. Scales are a really good indicator of salmon's age, and also we can derive something about the growth history of the animal from the scales. So the nice thing about scales is that we can take them without actually harming the fish. But if you've ever caught a fish for your supper, you might want to have a go at actually extracting another structure that grows just like the scales. These are called otoliths, or ear stones, and they actually grow, they're little tiny crystals, and they grow in either side of the head of the fish. They function actually in hearing and balance of the fish. And they're made of calcium carbonate, which is like a hardened form of chalk. This is an otolith from an adult one-sea winter fish, and here are some just for comparison. For example, from a smolt. So that's little tiny crystal is from a smolt about 12 centimeters long. And these structures, as they grow, the minerals of the calcium carbonate incorporate information about the elemental concentrations that are part of the water where the fish is actually living. So for example, if we look at elemental concentrations in the portion of the otolith which was actually formed when the fish was a smolt, it relates very well to the elemental concentrations of the water where they were born. So you can work out something about where that animal was from, or what catchment that animal was from. When we look at otoliths from adults, which is what I'm quite interested in, we can look at the atomic ratios of elements like oxygen. And oxygen in particular, we use really high resolution, sophisticated instruments to extract really high resolution profile of the oxygen atomic ratios. And that tells us something about the water temperature where the fish was inhabiting. So if we look at the adult portion of the otolith, which was grown while the fish was at sea, it's kind of this outer bit of the otolith, and we look at the oxygen profile in that bit of the otolith, we can then translate that into water temperature. So you can see here we've extracted these inferred water temperatures from a fish that left from the north coast of Scotland, traveled into warmer waters before traveling back into colder waters, spending a period of about 3 months into cool waters before moving again into warmer waters before it was caught in July of 2009, again on the north coast of Scotland. So we know quite a lot about the water temperature at the surface of the ocean out in the Northeast Atlantic from satellite and from instruments that are actually in situ. And from this information, we've developed, with my colleagues at the University of St. Andrews, a really simple model to predict from the information that we get in the otolith something about where those fish might have been at sea. This model can only resolve latitudinal bands, but it shows how the temperature profile that I just showed you could translate into latitudinal migrations. So in this model, each box represents a possible match between what we've observed in the otolith and what we've observed out at sea. And at each time step, we match up what we've seen in the otolith with what is actually out at sea. So you can see how that temperature profile turns into or translates into this fish migrating again from the north coast of Scotland up into the northeastern Atlantic, staying again in cooler waters for around 3 months before returning back home to be caught. So this is one way that we're studying salmon at sea, an indirect way of studying salmon at sea, using these little natural data storage tags like otoliths and scales. And by looking at the long-term changes in the ocean migration of salmon, we might better be able to understand their responses and adaptations to those changes. and perhaps improve salmon management here at home. Every fish has a story to tell about where it's been or where it's from and how well it grew while it's at sea. We just need the tools to be able to decode that information, which is what we're trying to do.